February 1943, North Africa. A German reconnaissance crew climbed into a captured American tank and started the engine. Their orders were simple: drive this Sherman 350 kilometers across the desert to the coast. 4.5 days. They expected it to break down. German tanks always did. After 50 kilometers, nothing failed. After 100, the engine still ran cool. After 200, the transmission still shifted smoothly. By the time they reached the port at Sfax, these experienced panzer crews were deeply worried. Not because the American tank had problems, because it had none. And if this was what American factories were building by the thousands, Germany had already lost a war it didn't know it was fighting. What German engineers discovered when they tested this single tank would trigger a crisis that echoed through their armored divisions until Berlin fell. The battle at Sidi Bou Zid had been a tactical victory for German forces. American units, new to combat in North Africa, had been pushed back. But wars aren't won by tactics alone. One M4A1 Sherman sat abandoned in the sand, its American star still visible on the hull. Someone had painted War Daddy 2 on the side, serial number USA 3067641, built by Lima Locomotive Works in Ohio. It had belonged to Company G of the 1st Armored Regiment, 1st Armored Division. The crew had bailed out, leaving the tank intact. Officers from Heavy Panzer Battalion 501 gathered around it with notebooks already open. The Army Weapons Office had issued standing orders about captured American equipment. Anything operational goes to the testing facility at Kummersdorf. No exceptions. A reconnaissance unit got the assignment. Drive this Sherman to the port at Sfax, 350 kilometers across North African terrain. Load it onto a ship bound for Germany. The crew climbed in, expecting a short trip. German tanks needed constant maintenance. The Panzer III required stops every few hours. The Panzer IV overheated in desert conditions. The Tiger, Germany's most powerful tank, broke down so often that recovery vehicles followed it everywhere. They started the Continental R975 radial engine. It caught immediately. The sound was different from German engines. Smoother, somehow. First gear engaged without grinding. The transmission felt strange to the driver. Too easy. German transmissions required double clutching, careful throttle management, precise timing. This one shifted like a civilian truck. 10 kilometers passed, then 20. The engine temperature stayed stable. German tanks would be showing heat stress by now. 50 kilometers. Nothing failed. The crew stopped for the night, ran their checks. The oil pressure was fine. The cooling system hadn't leaked. The tracks showed normal wear. They found nothing wrong. Day 2. The terrain got rougher. Rocky ground that should have stressed the suspension. The Sherman absorbed it without complaint. 100 kilometers. The transmission still shifted smoothly through all 5 forward gears. No grinding, no mischiered shifts. The synchronized gears made it almost impossible to make a mistake. 150 kilometers. The crew started discussing what they were experiencing. This wasn't normal. German tank crews spent half their time on maintenance. This American tank just kept running. 200 kilometers. The engine had never overheated. Not once. The air filtration system handled desert sand without clogging. German tanks in North Africa suffered constant filter problems. By the time they reached Sfax port on day 4, they'd driven 350 kilometers. The Sherman had not required a single mechanical repair. Not one adjustment. Not one component replacement. The crew filed their report. Someone in the chain of command underlined a single sentence 3 times. Vehicle operated continuously without mechanical intervention. The ship's manifest listed one M4A1 Sherman tank. Destination: Kummersdorf, Proving Ground, Brandenburg, Germany. What waited there would expose a gap German industry couldn't close. Spring 1943. The cargo ship steamed north across the Mediterranean, past Sicily, through the Strait of Gibraltar. War Daddy 2 sat secured in the hold. Wehrmacht engineers had already prepared testing protocols, standard procedure for captured equipment: photograph everything, measure everything, test everything to destruction if necessary. But the Army Weapons Office had added unusual instructions. This tank must reach Kummersdorf intact and operational. No destructive testing until comprehensive automotive evaluation was complete. German intelligence had numbers about American tank production. But numbers on paper meant nothing compared to the physical vehicle being transported toward Berlin. The ship docked in Germany. Rail transport carried the Sherman to Kummersdorf, located 25 kilometers south of Berlin. This facility served as Germany's primary proving ground for both German and captured Allied equipment. The Sherman rolled off the transport car bearing new markings. German designation: Beutepanzer 259. License plate: WH058941. Test engineers immediately stenciled armor thickness measurements across every surface. Angles and dimensions covered the hull and turret. They photographed it from dozens of angles before anyone even started the engine. Teams assembled: powertrain specialists, armor experts, weapons evaluators, automotive engineers. Each group had specific testing protocols to complete. The transmission team approached first. They'd read field reports from the reconnaissance crew, 350 kilometers without problems. That seemed impossible based on German tank experience. One engineer opened the transmission housing. What he saw made him call over his supervisor. The gears weren't cut like German gears. Instead of straight teeth that required precise tolerances and constant maintenance, these gears had teeth cut at angles. Herringbone pattern, like fingers interlocking. This design distributed stress across multiple teeth simultaneously. German engineers knew about herringbone gears. They'd considered them too difficult to mass-produce, given their industrial capabilities. The Americans had been manufacturing them by the thousands. The testing was about to begin. The results would contradict everything German tank doctrine assumed about necessary trade-offs between performance and reliability. The first automotive trials started simple: drive the Sherman through obstacle courses designed to replicate battlefield conditions. Measure fuel consumption, monitor engine temperatures, record transmission behavior under varying loads. After each trial, engineers disassembled components to examine wear patterns. They looked for stress signs, inadequate lubrication, design weaknesses. The Sherman performed adequately in every category, but it excelled in the one metric German tanks consistently failed: operational endurance without maintenance intervention. The transmission became an obsession for German powertrain specialists. It featured 5 forward speeds plus 1 reverse. Gears 2 through 5 had synchronization that eliminated double clutching during normal operations. This made the tank nearly as easy to drive as civilian automobiles. Minimal specialized training required. Any soldier with basic automotive knowledge could operate it. German tank drivers, by contrast, spent weeks learning complex double-clutching techniques and careful throttle management. Mistakes damaged the transmission. Expensive mistakes. One test engineer wrote in his report, "Design assumes ordinary soldiers will operate these machines. German designs assumed highly trained specialists would always be available. The Continental R975 radial engine demonstrated remarkable tolerance for varied operating conditions. Engineers ran temperature tests across ranges that would cause German engines to overheat or lose power. The cooling system was simple in design, almost crude compared to German systems, but it proved highly effective. The air filtration system handled desert sand without the frequent clogging that plagued German tanks in North Africa. German units had filed hundreds of reports about filter failures in sandy conditions. Every system reflected the same philosophy: practical functionality over theoretical optimization. Extended range testing began in late spring. Engineers drove WWII through trials designed to stress every mechanical system. They documented operational range exceeding 2,000 kilometers before requiring major maintenance. German Panther tanks, Germany's newest medium tank design, required major maintenance every 500 kilometers, sometimes less. The math was simple and brutal. One Sherman could operate 4 times longer than one Panther before needing workshop-level repairs. Transmission efficiency measurements showed power losses through the Sherman drivetrain significantly lower than comparable German systems. More engine power reached the tracks. Less was wasted as heat and friction. The synchronized manual transmission made gear changing smooth and simple. No double clutching. No careful rev matching. The driver just moved the shifter. German transmissions in the Panther and Tiger required both skill and luck. Even experienced drivers sometimes missed shifts and ground gears. Each mistake wore components that were already operating at their design limits. But the final drives revealed the most damning comparison. German Panther tanks employed final drive systems inherited from the Tiger design, straight-cut gears in housings that proved inadequate for the loads imposed by the 45-ton vehicle. Field reports from North Africa and the Eastern Front documented final drive breakdowns, forcing Panthers to be abandoned after relatively short movements, sometimes less than 100 kilometers. The Sherman's final drives used the same herringbone gear principles as the transmission. They rarely failed, even under sustained combat conditions that destroyed German components. Test engineers disassembled Sherman final drives, expecting to find wear that explained the 350-kilometer drive from Sidi Bouzid. They found normal wear patterns, nothing excessive, nothing concerning. These components had margin built in, lots of margin. By summer 1943, Kummersdorf had accumulated enough data for preliminary internal reports. The conclusions were sobering for anyone who read them objectively. June 6, 1943, Hillersleben Artillery Range. Reich Minister Albert Speer arrived to preside over a major armament conference. Leaders from the armaments industry filled the viewing stands. Senior Wehrmacht officers lined the front rows. The demonstration program included hill-climbing trials. War Daddy 2 sat at the base of a test slope alongside Germany's latest designs. Next to it, a Panther Ausf D, fresh from production. Germany's answer to the Soviet T-34, 700 horsepower Maybach HL-230 engine. Thick frontal armor, powerful 75mm gun. Beyond that, a Ferdinand tank destroyer, 65 tons, electric transmission. Germany's most advanced armored fighting vehicle. Speer needed to understand what American industry could produce and how German designs measured against enemy equipment. The Sherman went first. The driver started the engine, engaged first gear, began climbing. The transmission shifted through second, third, fourth, smooth, confident. The tank crested the hill without drama. Watching officers nodded. Adequate performance. Nothing impressive. But nothing wrong either. The Panther followed. Its more powerful engine should have made this easy. The driver pushed harder than the Sherman driver had. The engine roared. The Panther clawed its way up, throwing dirt from its tracks. It made the climb. Barely. With considerably more difficulty than the lighter American tank. Then came Germany's pride, the Ferdinand. 65 tons of armor and firepower. The most technologically sophisticated tank destroyer Germany had built. The electric transmission whined. The massive vehicle started up the slope. Halfway up, the drive motors stalled. The Ferdinand sat motionless on the incline. Engine running, but unable to move. Recovery crews scrambled. Officers in the viewing stands shifted uncomfortably. Speer watched without expression. This was happening before dozens of senior officers and industrial leaders. An embarrassing failure of Germany's most advanced armored vehicle, beaten by a tank built in American automobile factories. Speer would later write about Sherman capabilities he observed during inspection tours. He noted that reports on cross-country mobility had been very favorable. The Sherman climbed mountains German tank experts considered inaccessible to armor. He attributed this to the Sherman having very powerful motors in proportion to weight. Its cross-country mobility on level ground was definitely superior to German tanks. These observations came from Germany's armaments minister, the man personally accountable to Hitler for results. His written assessment appeared in Das Reich newspaper on June 27, 1943. The article called the Sherman a praiseworthy product of the North American steel industry. It mentioned the gyro-stabilized gun as the first attempt of its kind ever made anywhere, carefully worded for propaganda purposes. But the private alarms spreading through German engineering departments told a different story. American tanks weren't just adequate. They were fundamentally better engineered for sustained field operations. Back at Kummersdorf, systematic testing continued through summer and into autumn 1943. Engineers measured operational range in extended trials that pushed the vehicle to its limits. They documented operational ranges exceeding 2,000 kilometers before requiring major maintenance. Roughly 4 times what early model Panthers could achieve in field conditions. They measured transmission efficiency that exceeded any German tank. Power losses through the drivetrain were significantly lower than comparable German systems. They examined the synchronized manual transmission that made gear changing smooth and simple. No double clutching. No careful rev matching that German transmissions demanded. The final drives presented another revelation that challenged German engineering assumptions. Restoration projects, decades later, would find Sherman final drives that needed no mechanical restoration after years of storage. The design margins exceeded immediate requirements by substantial factors. By late 1943, Kummersdorf produced comprehensive internal reports that circulated through Wehrmacht technical branches. These documents, intended for senior Wehrmacht officers and armaments ministry officials, painted a sobering picture. The Sherman demonstrated American automotive engineering maturity that Germany fundamentally lacked, despite German theoretical knowledge and scientific expertise. Mass production techniques allowed tolerances that would be considered sloppy in German precision manufacturing. Yet they resulted in more reliable vehicles that functioned better under field conditions. Interchangeable parts meant field repairs could be accomplished with basic tools and minimal specialized training. German vehicles required factory-level precision and specialized equipment for many repairs. The entire design philosophy prioritized keeping vehicles operational rather than achieving theoretical performance maximums that looked impressive in specifications but couldn't be maintained in combat. Internal German engineering assessments documented observations about American industrial advantages that went beyond simple production numbers. American automotive engineering reflected decades of civilian industry experience. Before the war, the United States had widespread automobile ownership. Vehicles were commonplace among ordinary citizens across all economic classes. Germany had far more limited civilian automotive experience. Cars remained luxury items for the wealthy and party elite. The Volkswagen program, promised to German workers since 1934, had delivered fewer than 1,000 civilian vehicles by 1939. This vast difference in automotive industry maturity translated directly into tank design philosophy. Americans built tanks that mechanics with civilian automotive training could maintain using skills they already possessed. Germans built tanks that required specialist training and constant expert attention from personnel with years of specific military technical education. The comparison with German tank reliability became impossible to ignore as field reports accumulated through late 1943 and early 1940. Panther tanks required strict operational restrictions to prevent mechanical failures. Drivers received explicit instructions not to change gears frequently. Excessive shifting damaged the transmission. Third gear in particular broke often enough that field manuals warned against its use, except when absolutely necessary. Panthers could not turn while backing up. This would destroy the transmission. Pivot turns were only possible when ground resistance was equal on both tracks. This severely limited tactical flexibility. Foreign objects entering the running gear could jam the drive sprocket. Hours of maintenance required to clear them. These problems existed despite Panthers being built in dedicated tank factories by skilled workers using the best available materials Germany could provide. The Sherman, by contrast, had been designed by automotive engineers at General Motors, Ford, and Chrysler. They applied mass production principles developed over decades of civilian vehicle manufacturing. The tank incorporated commercial automotive components wherever possible. This leveraged existing supply chains and manufacturing expertise. The transmission came from multiple manufacturers: Caterpillar Tractor, Buick, Ford Motor Company, all building to identical specifications with fully interchangeable parts that could be mixed freely without adjustment. This standardization, routine in American automotive industry, remained largely theoretical in German tank production. Each manufacturer introduced subtle variations that prevented true parts interchangeability. Additional captured Shermans arrived at Kummersdorf through 1943 and 1944. Tanks taken from British units in Italy, Soviet forces on the Eastern Front. Each underwent similar testing protocols. The British had refitted some Shermans with their 17-pounder anti-tank gun, the Firefly variant. German engineers examined these modified tanks with particular interest. The Sherman's large turret ring accommodated the significantly larger gun with minimal modification. Growth potential built into the original design. German engineers hadn't considered this when specifying their vehicles. The Panther, rushed into production to counter Soviet T-34 tanks, had no capacity for significant armament upgrades without complete turret and vehicle redesign. Reliability trials expanded to include tests specifically designed to replicate combat conditions. Engineers drove Shermans through hundreds of kilometers of cross-country movement. They recorded every mechanical incident, maintenance requirement, component failure. They compared these results with field reports from Panther and Tiger units operating on the Eastern and Italian fronts. The numbers told an unambiguous story. Panther operational readiness averaged below 40% through most of 1943. Some units reported catastrophic rates as low as 20 to 25%. Individual Panther battalions documented periods when fewer than 1 in 5 tanks were actually capable of combat operations. Sherman tanks maintained substantially higher operational availability across all theaters. Specific data from German field reports documented Panther reliability problems in devastating detail. July 1943, Operation Citadel at Kursk. Panthers achieved only 16% operational readiness. Mechanical failures eliminated more tanks than enemy action. December 1943, readiness improved to 37%. February 1944, still 37%. April 1944, reached 50%. May 1944, finally achieved 78%. These figures represented the percentage of Panthers actually capable of combat operations on any given day. The remainder sat broken down, awaiting parts, undergoing repairs. The progression showed gradual improvement as design flaws were addressed. But even the best Panther readiness rates never matched what Shermans achieved from initial production. By December 1943, the pattern had become undeniable to any objective observer. Engine lifespan for Sherman diesel variants exceeded 3,000 kilometers under proper maintenance. Panther engine lifespan barely reached 1,000 kilometers, even after improvements addressed the worst early problems. German reports from March 1944 documented that improved Panther engines achieved service life of 700 to 1,000 kilometers. This was presented as a success. The improvement merely brought Panther engines to roughly one-third of Sherman diesel capability. Sherman transmissions required minimal maintenance between overhauls. Synchronized gears made driver error less likely to cause damage. Panther transmissions demanded constant attention and frequent repair. Third-gear failures were so common that drivers learned to skip from second to fourth gear to avoid using the problematic ratio. Sherman final drives operated reliably under conditions that routinely destroyed Panther final drives within 100 to 200 kilometers of operation. Field reports from German units using captured Shermans reinforced the Kummersdorf testing data with real-world operational experience. German mechanized units desperate for reliable vehicles eagerly employed any captured American tanks they could obtain intact. Unlike Soviet T-34 tanks, which Germans modified extensively before use, Shermans entered German service without changes. They didn't require modification because they worked correctly as designed. German tank crews who had experienced multiple mechanical failures in their own vehicles found the Sherman's reliability remarkable. They commented on it frequently in letters and reports. Reports from panzer regiments noted that Sherman operators could focus on tactical considerations and combat effectiveness. Panther and Tiger crews constantly worried about reaching the battlefield without breakdown or completing missions before mechanical failure immobilized their vehicles. The 10th SS Panzer Division captured 12 M4A3 Shermans at Hatton in January 1945 during Operation Nordwind. These tanks had belonged to the American 43rd Tank Battalion. Crews had abandoned them during the German assault. The 12 Shermans were formed into the 13th Company of the 10th SS Panzer Regiment. They served in combat operations for the remainder of the war. These tanks served as reconnaissance vehicles and mobile reserves, roles that required sustained movement without maintenance stops and reliable mechanical performance. German commanders recognized what Kummersdorf testing had proven years earlier. American tanks could be relied upon to function when needed. This dependability, more than firepower or armor protection, determined tactical utility in the final months of the war. A Sherman arriving at the battlefield with an operational gun was infinitely more valuable than a Panther with superior firepower broken down 20 kilometers behind the lines. Then Allied bombers struck the target that would cripple German armor production. April 27, 1944. night, Royal Air Force Bomber Command launched 322 aircraft against the Maybach engine plant in Friedrichshafen. The raid destroyed the engine factory. The ZF gearbox factory adjacent to the engine plant also went up in flames. Production of tank engines and transmissions halted completely. For 6 months, not a single new Maybach engine or ZF transmission left the factories. When production finally resumed in November 1944, quality control had degraded significantly. Slave labor, increasingly employed in German tank factories as German workers, were conscripted for military service, introduced deliberate sabotage. Cigarette filters jammed in oil passages, gaskets installed incorrectly, components assembled without proper clearances. These problems never affected Sherman production. American factories sat safely thousands of miles from any combat zone, staffed by motivated workers earning good wages under decent conditions. January 23, 1945. The Panzer Commission report documented the final crisis. 500 defective final drives in Panzer IVs, 370 in Panthers, 100 in Tigers, approximately 200 failures in Hetzer tank destroyers. General Wolfgang Tomele, Chief of Staff of the Inspector General of Panzer Troops, wrote the assessment. In such circumstances, orderly utilization of tanks was simply impossible. The troops lost confidence in their vehicles and abandoned whole vehicles just because of final drive problems. Early 1945, Kummersdorf prepared for evacuation as Soviet forces advanced toward Berlin. Engineers frantically packed testing data, shipped documentation west. Some captured tanks, including at least 2 Shermans, were pressed into improvised service defending the approaches to Berlin. The Shermans continued operating until destroyed by enemy fire or abandoned when fuel ran out. The German tanks broke down from mechanical failures at rates that shocked even experienced crews. When West Germany's Bundeswehr developed the Leopard 1 tank in the 1950s, designers consciously emphasized reliability and maintainability over pure performance specifications. They studied American automotive engineering principles and deliberately applied them. War Daddy 2 had taught a lesson that took a decade to learn. And by then, it was far too late.